Hello, this is Darrell Lee Berry Jr. continuing with my review of the chapters I'll be taking a test on soon. So I'll continue where I left off. And finish chapter 2.3. And after that, move on to 2.2. Then after that, move on to 2.3. So that is the plan. So right now, we're here with the standard model, standard matrix of a linear transformation. So I know this is going to be something that's important. So we may spend some extra time on this and make sure that we get this worked out. So it says the standard matrix of a linear transformation. When we examine the previous example, and the previous example was the projection uh, as a matrix. Basically, backtracking from this, recognizing that it's x times that matrix. When we examine the previous example, we find a geometric meaning, the column vectors of the matrix. So geometric meaning of the columns. As we know, when we multiply a matrix by a vector, we get the appropriate linear combination of the columns of the matrix. So AX equals linear combination of matrix columns. And it gives us this example, which I shall write out. A11, A12, A21, A22, 10 equals A11, A21 plus 0 equals A11, A21, 2 by 2, 2 by 1. So we know we need a 2 by 1. And vice versa for A11, A12, A21, A22, 0, 1. This should give us the second column. A12, A22. Good so far. So we can see that the first column of A is the vector. The first column of A is the vector A1. Think about this. Oh, I see. The first column of A, the first column of the matrix A is that vector times the entire matrix A. That's just the first column of matrix A, okay? And the second column of A is the whole matrix A times that vector. So this is how we can extract columns from matrices. Turning this observation on its head, we note that we can find the matrix A and hence the linear map mu A by finding the two vectors mu A10 and mu A01 and just put them in their proper place. This seems surprising at first as the function mu A is completely determined by what it does to only two non-parallel vectors in R2. This is, in fact, a general property of linear maps. If, for example, T, the transformation is R2 to R2 is a linear transformation, is for any x vector x1, x2 in R2, we write x equals x110 plus x201. Okay, with it so far. And so by the linearity properties, the transformation of x equals the transformation of x110 plus x201. We're just plugging that in. So that equals x1 t 10 plus x2 t 01. And this is some property of matrices that I can't recall at the moment. Probably proposition 5.1 since I heard that so many times. Here we go. Here it is right here. Definition. At the beginning of 2.2 for linear transformations, the T plus distributes over sum and the distributes over scalar. That's linearity. That is, once we know the two vectors v1, interesting. So what they're now saying is this is x1 v1 plus x2 v2. So they're calling that transformation a vector. Thus v1 equals t10, v2 equals t01. Vector 1 is a transformation of 1, 0. We can determine, that is, once we know the two vectors v equals t10 and v2 equals t01, we can determine tx, every x in R2. Indeed, we can create a 2 by 2 matrix by inserting v1 as the first column and v2 as the second column. Then it follows from what we've done that t equals mu a. specifically if V1 equals A11, A12, and V2 equals A12, A22, then A equals V1, V2, and those are column vectors. So that equals A11, A12, A12, A22. Swap those. A is called the standard matrix for transformation. This entire discussion works more generally for linear transformations from Rn to Rm. We will postpone that to chapter 4. Warning, in order to apply the procedure we have just outlined, one must know in advance that the given function t is linear. If it is not, the matrix A constructed in this manner will not reproduce the original function t. So linearity is beginning of 2.2, linearity. The scalar can be pulled out and the sum distributes. If it's linear, you can construct the original matrix from these vectors. Okay? We'll see how this works. Example 5. Okay? L is spanned by 1, 2, and projection onto the line is R2 to R2. We checked in example 1C that this is a linear map. Thus, we can find the standard matrix for the projection onto L. To do this, we compute the projection. That's the standard matrix for that single vector equals right? So y 1/5 and p 0, 1 equals 2/5, 1, 2. For the standard matrix representing the projection of the L, A equals 1/5, 2/5, 2/5, 4/5 equals 1/5, 1, 2, 2, 4. The only thing I'm not sure about is where the 1/5 is coming from. So let's go back to example 1C. Here we go. So now the projection is linear because of this. And we did this earlier, which means like yesterday or something. So the projection with the dot product and vector squared distributes just the same. I'm just not sure where the 1/5 is coming from. That is the only thing. Because we know that the reflection across L is given by the reflection onto L is 2, the projection of the L minus the identity matrix. The standard matrix for RL will be B equals 2 times projection onto L minus the identity matrix. It equals 1/5, 3, 4, 4, 3. We actually need to define the matrix for reflection across a general line in exercise 12. Right, on to example 6. All right, generalizing example 2C, we consider the matrix A theta equals cosine theta, sine theta, negative sine theta, cosine theta. We see that A theta 1, 0 equals cosine theta, sine theta, and A theta 0, 1 equals negative sine theta, cosine theta. So this is just pulling out the columns as a function of whatever A is times that portion of the identity. Okay, I'll put them there. As pictured in 2.8. Thus, the function u theta, A theta, rotates 1, 0 and 0, 1 through theta. And we strongly suspect that mu A theta x equals AX A theta x. Should be the vector obtained by rotating x triangle theta. Equals x rotated through theta. We'll leave it to the reader to check in exercise 8 that this is the case, and we call it a rotation matrix. Rotation matrix. So I do remember seeing something like this in my quantum mechanics class. I took it before taking this class. This was a bad idea. I'm gonna take that class again. And but I can see how I remember seeing this. Right? So 0, 1, 1, 0 transforms into negative sine theta, cosine theta, and cosine theta, sine theta, negative sine theta, cosine theta. So cosine theta, sine theta changes the first value, the x value, and negative sine theta, cosine theta changes the y value. All right? Through theta. Cosine of 0 is 1. Sine of 0 is 1. Cosine of 0 is 1. And sine of 0 is 0. So theta is 0, it doesn't rotate at all. Sine of 0 is 0. Cosine of 0 is 1. So that stays the same. Sine of 90 degrees is 1. Cosine of 90 degrees is 0. Sine of 90 degrees is 1. So the x1 rotates. And negative sine of 0 is negative 1. Cosine of 0 is 0. So the y rotates. On the other hand, we could equally well have started with the map T theta R2 to R2 and defined by rotating each vector counterclockwise by the angle theta. Take a geometric definition. The length of the transformation of theta of x is the same as the length of x, and the angle between them is theta. Why is this map linear? Here's a detailed geometric justification. It is clear that if we rotate x and then multiply by a scalar c, we get the same result as rotating the vector cx. Officially, the vector has the right length and makes a right angle with cx. Now, as indicated in figure 2.9, and I'll enlarge the book. Now, as indicated in figure 2.9, since the angle between the transformation by theta of x and the transformation by theta of y equals the angle between x and y, because they both uh, uh, shift x and y by the same amount because it's by the same angle theta. And since lengths are preserved, it follows from side congruence theorem that the shaded triangles are congruent, and hence the parallelogram spanned by x and y is congruent to the parallelogram spanned by the transformation by theta of x and the transformation by theta of y. The angle between the transformation theta of x plus the transformation theta of y and the transformated theta x is the same as the angle between x plus y and x. Makes sense? So by simple arithmetic, the angle between the transformation theta of x and the transformation theta of y and x plus y is theta. You know what I mean? That's apparent because just like how the two subvectors rotate by the same amount, their sum would definitely have to rotate by the same amount, which would be the same amount of difference between these sums and the differences of the non-rotated. Again, because the parallelograms are congruent, T transformation by theta of x and transformation by theta of y has the same length as x plus y. Hence the same length as the transformation of theta x plus y. And so the vectors transformation theta of x and transformation theta of y and transformation theta of x plus y must equal. Ooh. Seems like it's making it word more complicated than it needs to be, but it could be just me. The natural question to ask is this: what is the product of a theta, a phi? The answer should be quite clear if we think of this as a composition of functions. Mu a theta a phi equals mu a theta encompassing mu a phi. Leave this to exercise 7. Okay. So example 7. The geometric interpretation of a given linear transformation is not always easy to determine just by looking at the matrix. So we have A equals 1/5, 2/5, 2/5, 4/5. We might observe that for every x in R2, AX is a scalar multiple of 1, 2. Let's take a look at this. For every x in R2, A times x is a scalar multiple of the vector 1, 2. All right, let's test that. So if x equals 1, 2, AX equals 1/5 plus 4/5 and 2/5 plus 8/5 equals 5/5 and 10/5. So that equals 1, 2. And let's say we have x equals 3, 5. AX equals 3, 5 plus 10, 5, and 6, 5 plus 25. So that equals 13, 5, and 26, 5. And that is what? Did I multiply that correctly? Doing it fast. Right? So that equals 13 times 1/5 and 2/5. Oh, so that equals 13/5 times 1. Yep, it is a scalar multiple of 1, 2. All right. Why that is? Well, A equals 1/5 times 1, 2, 2, 4. That makes it a scalar of 1, 2. Well, I do see that, I see. So this relates to the first vector, and this relates to the second, or at least the row, the first row of x, second row of x. And we see that whatever it is, that column is twice the left column. So you can see how is a scalar of 1, 2. A little bit, I can see. From past experience, what this suggests, as a clue to understand the associated linear transformation, we might try calculating A2, and we find that A2 equals A, or A squared equals A. It follows that AN equals A for all positive integers n. What is a geometric explanation? With some care, we can unravel the mystery. So A x1, x2 equals 1/5, 2/5, 2/5, 4/5, x1, x2 equals x1, 5, 2x2, 5, x1, 2x1, 5, 4x2, 5, and that's plus. So that equals 1/5 x1 plus 2x2 and 1/2 x1 plus 2x2 equals, all right, let's check this one out. So this is the same thing, except there's a 1 here and a 2 here. And now, I make this 1/5 x1 plus 2x2. And that equals right. Let's see. My pad froze. One moment here. So that was 1, 2 times 1/5 x1 plus 2x2. So that equals 1, 2 x1 plus 2x2 over 5. Now I'm seeing where the 5 comes from, the 1/5. So that's 1, 2 x1 x2 dot 1, 2 over 5. So that equals x dot 1, 2 over, that's the square root of 1 squared plus 1 squared is plus 2 squared. So that equals, it still times the vector. So that equals x dot 1, 2 over the magnitude of 1, 2 squared, 1, 2. Now we see where the 1/5 comes from, because we were using the vector 1, 2, and this becomes projection onto 1, 2 of x, a definition. Projection of x onto the line spanned by 1, 2 equals projection onto L of x, L span 1, 2. All right. Of course, when one remembers example 5, this is really no mystery. This explains why a squared x equals ax for every x in R2, and ax squared x equals ax. And once you projected the vector x onto the line, it stays put. All right. So it just keeps putting it right back on the same line, so it can't go anywhere. That's why the matrix, that's why it stays the same. All right. So we have reached the problems on 2.2. I'll go ahead and stop here. And what I'll do is take a break and come back. And then we'll have time to do 3.2. And then tomorrow I can focus on problems. That is the plan. Come back, 3.2, so I can get some problems done today. How long is 3.2? Let me see. 3.2, the four fundamental subspaces. It's not long at all. 1, 2, 3, 4, 5, 6. 6 pages. So we'll do that. I'll take a break and then we'll take care of those 6 pages. Then I'll take a longer break and then we shall do some problems. Maybe I can get you all the problems today and then do some more problems tomorrow. So come back about 15 minutes. See you then.